Good evening, everybody. So, continuing from the last lecture, today we are again going to see three or four more work done by researchers. So, the today's work that I'm going to start is with Farm et al. So, Farm et al. Also developed a comprehensive algorithm in order to obtain the optimal orientation for the part to be fabricated. And he developed this for the stereolithography process. He developed it for the stereolithography process. And their methodology was basically called as the decision support system. Their methodology was named as the decision support system. So, in their system, basically, the user could select one or more options among the features. Now, what were those features that he specified were user specified critical surfaces, the coordinate systems, holes, cuts, shaft, protrusions, shells, and axes as per the need to select the candidate part deposition orientations. So out of these different options like critical surfaces, coordinate systems, holes, protrusions, intrusions, shafts, shells, etc., you could select some features out of these, and then the unit vector in the build direction of each candidate part was stored. The unit vector in the build direction for each part candidate deposition orientation was stored. So for every surface there was a unit vector, and the unit vector in the component of the unit vector in the direction of fabrication was basically stored as the candidate part deposition orientation. Now what happened was, these were the process parameters. Actually, these you can call as the process parameters. And out of these selected process parameters, now each selected orientation, which is now called as the candidate orientation, was compared on the basis of overhanging area, volume of support structure, build time, cost of the part, and problematic features. So each candidate orientation that you selected based in the Z direction. Now this is the direction of fabrication. This is the direction of fabrication. So out of all the candidate deposition orientations, the Z-axis direction was taken as the direction of fabrication. Now for each orientation, the comparison was made on the basis of overhanging area, volume of support structure, build time, cost of the part, and problematic features. Now, what happened was, for each of the candidate criteria, you assigned weights, and a position score was assigned. For each candidate, like you came up with five conditions, or five probable orientations, rather, five probable orientations. And now for each orientation based on these five constraints, you define the probable score by assigning weightage to them. Now, once a weightage has been assigned to each preference for each criteria, okay, once the weightage has been assigned to each preference to each criteria, now the final score of each orientation, like in the example, I am having five orientations. So for each orientation, the final score was calculated, and this was calculated by summing the multiplication of criteria weight and the position score of that individual criteria. So for overhanging area, what was the weightage you gave for orientation 1? For volume, whatever criteria weight you assigned for factor 1, build time, cost, and problematic. So based on this score, you basically tried to obtain the final score, and the maximum score was considered to be the most suitable part deposition orientation. Now, the problem that came in this algorithm was, if you have a part, say if you have a part like this, which is a simple cube, and you have not a through hole, but say if you look from the side view of this cube, you have a cavity which is going to a certain depth, but not going through the system. So if a viewer is observing this from the top view, if the viewer is observing it from the top view, he will not be able to see the cavity. He can only see the cavity from the front view. He can only see the cavity from the front view. So now if you look from the front view, you have basically a shell, and you also have cuts and holes in the system. But if you are looking from the top view, the cuts and holes are not available or not visualized. So deciding on the proper orientation of the part also becomes very critical over here. So when you are selecting the orientation in order to determine the features, it becomes very essential that you observe all the axes, or rather all the 6 views, before you decided on the proper final view through which you are going to develop the part. So this algorithm in itself took a very long time to compute, because it had lot of criterias to be satisfied, and the number of probable options were huge. So the number of calculations that were needed to come up with the final score was large. And there was a very good chance that some of the surfaces may actually be missed out if you are not having a proper orientation. Another thing can be, in order to remain safe with the orientation point of view, what people started doing was they started taking all the possible orientations that could be taken in the system. They started taking all the possible orientations. So what started happening was that the number of computation points became huge, and this algorithm was not very useful in giving an optimal value, because the pre-selected orientations were generally user defined. So within the user defined function, it gave the best orientation. It is not optimal orientation. It is not an optimal orientation. So this methodology, although was successful with stereolithography, it was not found to be very feasible with FDM and SLS. So another research work, which was based on the primitive approach that you saw during the CAD solid modeling, that is primitive instancing, was done by Professor Masood and his co-workers. They published a series of papers from 2000 to 2003, and their approach was actually called as the volumetric error-based approach. It's a very simple approach. Generally, what would you have is a simulation software. You would have a simulation software, something like what we do as of today. We have simulation softwares where we observe the complete fabrication process. So using the simulation software, I can very easily find, like, if this is the part I have, I can find out what is the volume of the CAD model. And using the simulation software, what is the volume of simulated model? So now, for every possible orientation that I can think of, I can simulate that model in that orientation, and I can always find out using my simulation software what will be the volume at that individual orientation. So there is generally going to be a difference, definitely, in volume between the CAD model and the simulated model, because first of all, the model in the simulation is going to be fabricated in stairs. And another thing was, the build edges were considered to be rectangular in nature. As a result, you had staircasing and surface roughness. You had staircasing and surface roughness. So volumetric approach method, volumetric error based approach basically meant that you calculated the volume of the CAD model, and volume of fabricated model, that is simulated. That is not fabricated but simulated. Now, the difference of these two values has to be minimum, to decide the suitable orientation, So basically the concept is pretty simple, that you have the volume of CAD model and then you have the volume of the fabricated model. At whatever orientation, this difference of this value becomes minimum. That is the suitable orientation of fabrication. In real-time analysis, this becomes very easy to understand that yes, this is possible. But here, there are some basic concepts which are not being taken into consideration also. Support is not being considered. Support is not being considered at all. You are not considering the support structure generation in this evaluation anywhere. Secondly, when the tessellation of the CAD model happens, there is bound to be bound to have a volumetric error, and then during the fabrication stage, due to varying layer thicknesses, you can have even bigger volumetric error. So the layering process is considered to be uniform. So this method actually gave a far simplistic view of understanding how to define the part orientation, but there were some other constraints which were neglected in this process, especially the support structure. So they modified this work later on, and they also added the concept of support structure in the system. And this method was generally found to be very true in many softwares which were implemented during 2005 to 2015. Many softwares use this concept of minimum volumetric error. Then another method came from West. It came in 2001, and they actually used a simple mathematical equation in order to improve the build performance. And the build performance was shorter build time, better accuracy, and higher surface finish in stereolithography parts. So what they did was they planned the process by considering only 3 steps. The 3 steps were orientation, slicing, and process parameter selection. And the process parameters that they generally selected was layer thickness, sweep period, Z height, overcuring, and hatch overcuring. And part deposition orientation became an automatic selection for the process parameters because orientation study was being done over here. So what they did was they developed a module. Where all the surfaces that were there present in the CAD model, were divided into 3 basic surfaces. The 3 basic surfaces were planar surface, conical surface, and cylindrical surfaces. And based on these 3 surfaces, the most feasible orientations were planned. And based on these 3 type of surfaces, the most feasible orientations were planned. Now again, this work basically again entails us or takes us back to the work of FAM, where the most feasible orientation is actually going to be defined by the user, and it becomes a user defined function, and therefore the orientations become a user defined function. Now, once you had the most feasible orientation based on these three types of surfaces, the part is oriented along these pre-selected orientations, and then the slicing is done uniformly. And the slicing was done uniformly for the three objectives. What were the objective? Lower build time, better accuracy, and higher surface finish. Now, what they found was, since stereolithography process uses liquid resin. So what happens is that once you are making a part, and if you are making a hollow part, lot of liquid resin actually gets entrapped within the shell of the model, within the shell of the model. So support structure trapped volume actually becomes very important, because this volume, if it remains trapped inside, it increases the overall weight of the system. Suppose if we are making a hollow part, something like this, this is pretty simple thing. This is the walls which is going to be fabricated, and it is hollow over here. So what will happen is liquid resin will fill this structure, will fill this space, and the overall weight of this part, will become higher. Weight is higher because of entrapped volume. And why this volume has entrapped? Because it was acting as a support for the top layer, because it was filling up to act as a support for the top layer. So support structure trapped volume plays a very important role. Then secondly, if there is a large horizontal plane, then what happens is the laser actually cures the large surface like this. It goes like this. And as a result, what happens is between two hatchings, these are called hatchings, and this is called as hatch spacing. This is called as hatch spacing. So if the laser is not able to cover the complete hatch spacing, then some part of the liquid will remain uncured. That means it will not be solidified. So large horizontal planes have to be avoided. So now if you are making a part like this, you have a larger horizontal plane. So it is recommended that you make a part like this. Now, once you make a part like this, these two shell boundaries are going to be very thin. So that means if you have a small or a thin feature, you need to reinforce it. So the constraints of stereolithography were very huge. So even if you decided on some pre-selected orientations, you still had to keep in mind how these constraints are going to be satisfied. That is, support structure trapped volume has to be minimized, large horizontal planes have to be minimized, and thin features or small features have to be reinforced. So based on all these criteria, you can come up with four most feasible orientations. Now, out of these four orientations, it is your guess how you want to make it. Whichever orientation you feel like, you can use it. But this also created a lot of problems. This algorithm also creates a lot of problems, because support structure trapped volume and large horizontal surfaces are sometimes it is not possible to eliminate them at all. And this creates a lot of problems during the trade-offs. So now if you have a larger z height and a smaller horizontal surface, then hatch overcuring generally tends to occur. So now out of 6 process variables, you are trying to control those process variables also, while also taking care of constraints. It became very difficult for people to define the optimal orientation. And most of the times what was found was that whatever out of these four you took, out, the process plan was not always going to be optimal. the process plan was not always going to be optimal. Hence, this work was, although this work was published, but it was not implemented in any of the algorithms that was developed later on. Then in 2006, Dr. Pandey developed a system for determining orientation of FDM parts. So he considered the average part, surface roughness, and build time as the primary objective functions. So this work was focused mainly on FDM parts, and later it was found that this algorithm actually works very well for SL as well as for SLS also. SLS is selective laser sintering. I'll explain that when I'll do the process. So it also worked very well for SL as well as SLS processes also. Now, first of all, what he postulated was that the surface roughness for fuse deposition modeling is actually based on measuring the surface profile, is actually based on the measurement of surface profile, and the surface profile that he considered was RA, that is the average surface roughness of the part. So now if you had something like this, made, so you measured the surface roughness of this phase and you measured the surface roughness of this phase, and the average surface roughness was taken into consideration. So if you are having, say, 20 parts like this, so if you are having 20 parts like this, so what you ended up having was a proper model which can be developed, a proper surface roughness model can be developed based on the measured surface profile. Secondly, what he also did was he incorporated adaptive slicing. He incorporated adaptive slicing for the tessellated CAD models. He adopted the adaptive slicing concept. Now, in adaptive slicing concept, there has to be a limited surface roughness value criteria, because if you take cusp height, as the criteria for adaptive slicing, what will happen is you will get different cusp heights. And different cusp heights means different surface roughness. So it becomes very difficult to select the optimal surface roughness that you will take. So what they did was they incorporated the real-time adaptive slicing algorithm, where limited surface roughness value was taken as the criteria. So if you used adaptive slicing, you had different cusp heights. Based on different cusp heights, you had different RA values. Okay, you had different RA values. So based on the limiting value, that like you propose that RA, anything of RA less than 25 micron is acceptable to me. So 25 micron becomes your limiting value. So he used this concept of limiting surface roughness rather than limiting cusp height as the criteria. And the average part surface roughness was calculated using this expression, that is the surface roughness of each layer multiplied by the area of each layer and its cumulative divided by the cumulative surface area of the model. Now, build time was assessed as the number of adaptive slicing, and the consideration for support structure on build time was carried out by weighing the number of slices to the ratio of fraction of the supported area. So what he considered as build time was slices as well as support, So slices and support were both considered in considering the build time. And the assessment of build time was done by the following expression. TE is equal to N1 1 plus F into DS, where TE is the measure of build time, N1 is the number of adaptive slices, DS is the density of support material, and F is the ratio of supported faces of CAD model to the total surface area of the part. And they developed basically an algorithm using NSGA2 of multi-objective optimization. This is a part of artificial neural networks. It is an algorithm of ANN, And using this algorithm, they solved this problem of build time as well as the average surface roughness. Now, the average part surface roughness and build time were considered as two objectives, and Pareto optimal solutions, that is axis vector and angle of rotation, were obtained among all the possible solutions. Now what happened was, based on this algorithm that they had developed, they obtained different values of surface roughness and build time for each orientation. Each orientation, just like FAM did, for each orientation. Now for each orientation, you got these two values because of two objective functions. And based on this, either using the Pareto graph, either using the Pareto graphs, or by using the axis of rotation method, that is the Pareto optimal solution, that is what we call as Pareto optimal solution, where the optimal value is obtained based on the graph that is plotted for each orientation. So on one axis you had angle, and on the other axis you had RA and BT, and a graph was plotted. Based on this graph, whichever angle gave the best value within the constraint boundary, you defined that, you took that value as the optimal solution for the orientation. Now they also ended with defining a value of surface roughness, and the surface roughness was actually correlated with respect to layer thickness also. They also ended up having the correlation of surface roughness with layer thickness, and this correlation is actually provided in the slicing lecture that I have provided to you. So this correlation of RA with layer thickness is provided in the slicing slides. So this is all about the orientation studies.